Solution. Resolving the T2 and the T1 into horizontal and vertical components above, you have the sum of fx is equals to 0 and sum of fy is equals to 0. T2 cos 30 is equals to T1 cos 45. This will be our equation 1. T2 sin 30 plus T1 sin 45 is equals to 20. This will now be our equation 2. Solving equations 1 and 2 will give T2 is equals to, in bracket, T1 cos 45 all over cos 30 is equals to, in bracket, T1 times 1 over square root of 2 all over, open bracket, square of 3 over 2, close bracket. T2 is now equal to T1 times 2 all over, in bracket, square root of 2 times square root of 3, which will now give us equal to, in bracket, 2 over square root of 6 times T1. Substituting in equation 2, then we have that, in bracket, T2 over square root of 6 close bracket T2 times half plus T1 half 1 over square root of 2 is equals to 20. 0.408 T1 plus 0.707 T1 is now equals to 20. 1.115 T1 is equals to 20. Therefore, T1 is now equal to 20 over 1.115, which gives us 17.94 Newton. So T2 will now be equal to 2 over square root of 2 times 17.94, which will give us 14.6 Newton. Resultant velocity using vector representation. If a boy is running along the deck of a ship in a direction OA and the ship is moving in a direction OB, the boy will move relatively t the c along a direction OC between OA and OB. Figure 1.23. Now, in 1 second, the boat moves from O to B, where OB represents the velocity of the boy in magnitude and direction. Thus, in 1 second, the net effect relative to the C is that the boy moves from O to C. It can now be seen that if the lines OB are drawn to represent in magnitude and direction the respective velocity of the body and the boy and the ship, the magnitude and direction of resultant velocity of the boy is represented by the diagonal OC of the completed parallelogram having OA, OB as 2 of each size. OACB is known as parallelogram of velocities. Conversely, a velocity represented completely by OC can be regarded as having an effective part or component represented by OA and other components represented by OB. Figure 123 resultant velocity I force x is being drawn at an angle of 30 degrees. ABO represents the relative velocity. Example 4. A swimmer whose velocity in still water is 4 km per hour set out a straight angle to the bank of a river which is flowing at 3 km per hour. Draw a sketch of his path showing the water. Calculate his actual velocity through the water. Solution. Since the man is moving in 4 km/h. Then he now moves from O to A. Then, meanwhile, the river is flowing with a velocity of 3 km/h, moving from A to B. Then the resultant of the movement of the man is OB. But according to the law of vector resolution, forces start where the force ends. So, since the man is moving in the direction of AB, AO, the AO will now represent the movement of the vector or the direction of the man, followed by AB, which is the direction of the stream, which is moving at 3 km/h. Then OB will now represent the resultant of the movement of the vector. Since OAB is right angle triangle, the actual velocity through the water is given by OB equal to square root of square of OA square plus AB square, which is equal to square root of 4 squared plus 3 squared, which is equal to square root of 25, which will give us 5 km/h. Total also tan theta is equal to AB over OA, which is equal to 3 over 4, will give us 0.95. Theta, tan inverse of 0.95 will give us theta, which is equal to 36.86 degrees. Thus, the swimmer will move along the direction OB relative to the flowing river, where OB is at 36.86 degrees to OAO. Projectile. A projectile motion is one that follows a parabolic path. It is due to two independent motions at right angle to each other. These motions are a horizontal uniform velocity and a horizontal free fall due to gravity. If a body is thrown off from a point 0 with a velocity u at an angle theta, it will follow a parabolic path on a horizontal range r along the x-axis of the horizontal axis. The vertical component of the motion will be u sine theta. Equations used in projectiles. In a projectile motion, if u is the initial velocity at angle theta to the horizontal, we therefore have that flight time t is equal to 2u sine theta over g. Maximum height h is equal to u squared sine squared theta all over 2g. Horizontal range r is equal to u squared sine 2 theta all over g. Please take note of these formulas. Proof. Let us consider a body launched with initial velocity u at an angle theta with the horizontal as shown in figure 1.2. Constant horizontal velocity us is equal to u cos theta. Equation 1. Initial velocity, vertical velocity vy is equal to u sine theta. Our equation 2. At the time t after projection, vertical velocity vy is equal to u sine theta minus gt. This is our equation 3. And the vertical distance y is equal to u sine theta times t minus half gt squared. Acceleration a is equal to minus g, since g acts downwards. If we put y equals to 0 in equation 3 and solve